Hello, I'm Theo Mandel from IBM Corporate Technical Education. I would like to introduce Dick Berry, who will talk about the background and philosophy behind the CUA architecture. Dick was the lead architect of CUA. I like to think of Dick as being the father of CUA.
It has been said that I'm the father of CUA. I have just one question. If I'm the father, who is the mother? Hello, I'm Dick Berry from the User Interface Technology Group in Boca Raton. I'd like to preface this presentation with some remarks about the progress that's been made in user interface design throughout the industry in the past several years. The intent is to help you put CUA in perspective and to give you some insight as to why CUA must evolve. It's a new realm of programming design and user interface design that we're getting into. The industry has been heading in that direction for some time, and that's one of the reasons why we point out that CUA is not a leading-edge, state-of-the-art implementation in the industry. It represents an attempt to catch up and head in the direction the rest of the industry is going. CUA's purpose is to establish a base so that over time we can develop a leadership position within the industry. But right now, we've got some catching up to do. You need to understand that. You also need to understand that we're talking about different ways of doing things in the area of application design and user interfaces. We're getting away from the traditional procedure-oriented straight-line program flow where the application issues input statements when it's ready for input and it issues output statements when it's ready to respond to users. We're now turning that around and are designing programs that are driven by users. Today, users click a mouse button while they are pointing at something. This causes an input to the program that the program better be ready to handle. It puts users in control. Start using these kinds of interfaces because they are the direction for IBM and the industry. This is why intelligent or programmable workstations in the form of personal computers are leading the way in the industry. They allow us to program with this application design style to create more interactive and responsive user interfaces. To get yourself up to date in this area, you should take every opportunity to learn about object-oriented programming, event-driven, and user-driven systems. If you see articles, read them. And if you have the opportunity to take courses in this area, do so. IBM Corporate Technical Education has developed a curriculum for systems application architecture. This course, Designing Common User Access Interfaces, is an integral part of the SAA curriculum described in this brochure. It is one of the 6 courses on SAA that are now being offered internally in IBM. The goal of this presentation is to give you an overview of the background and philosophy behind CUA. This is not going to be a detailed description of CUA. It's going to provide an overview of the architectural basis for CUA. This material and more detailed information are available in an IBM Systems Journal article I've written on CUA. The article is in a special issue on SAA published in mid-1988. To begin with, I want to reference some work done several years ago by Chris Rutkowski of Rising Star Industries. His work was published in Byte magazine in October 1982. Basically, Rutkowski asked himself the question, how have other products that have been very technologically innovative come to be consumer products? Did they go through some unique process? Did they evolve in such a way that they became usable by consumers or non-technicians in that particular technology? The automobile was one technology that he talks about in particular in his article. He identified 3 major phases of evolution that such products typically go through. The first is called the engineering phase. In this phase of product evolution, the engineers and technology specialists first identify the technology, look for the potential benefits of the technology, and start developing prototype products. They actually conceive the product, and they are also the first users of the product. During this point in the product's evolution cycle, you will see it appear in magazines like Popular Science as inventors' ideas. They propose these new ideas as the forefront of technology, and they predict that these products will be in the marketplace in the next few years. During this period, the product gains popular notice. For Rutkowski's analogy, the automobile, this happened prior to 1900. Inventors were experimenting with internal combustion engines, the primary new technology that contributed to the development of the automobile. That was before the turn of the century, and it led into the next phase, which is called the enthusiast phase. This phase is characterized by a group of enthusiasts who recognize the novelty and benefits of using the new technology. This period is characterized by the formation of user groups, publications, and magazines dedicated to users of these new devices. These users are typically not willing to undergo a great amount of difficulty, but they will put up with some of the quirks and idiosyncrasies of these products and their engineering designs. The enthusiasts recognize the usefulness of the product, and this is also the first group to be vocal about ease of use problems with the product. They give feedback to the designers about ways to improve it. You can begin to see parallels in the computer industry. By the way, this phase happened with automobiles after the turn of the century. People used to go out in their automobiles on weekend drives. They were used mainly for recreational purposes, like going on a picnic on weekends. They were not major forms of transportation, and certainly not necessities. They were luxury items for recreation. In the computer industry, I believe this phase started about the mid-1970s, especially with respect to personal computers. Byte magazine started up, and a lot of other PC magazines came along in the late 1970s and early 1980s. At that time, we saw the formation of PC users groups. What also happens during this phase is an increased demand because there is more public awareness. That increase in demand starts a cost spiral, which lowers the product's cost, increases the demand further, and so forth. This leads us into the consumer phase of product evolution. Look at the trend in computer prices over time. Finally, Rutkowski proposed that the product becomes accepted at the consumer level when feedback contributes to the product architecture such that usability problems are fixed, because users at the consumer level are not willing to put up with a product's ease of use problems. They are interested in using the product strictly as a tool to help them accomplish something else they are trying to do. We now use cars mainly to get somewhere. We drive them on weekend picnics because they get us to the picnic site quickly and easily. You can still find car clubs for the automobile aficionados, but mainly we look at the automobile as a mode of transportation. A degree of usability has been achieved with the automobile based on standardization of a number of its components, so that all of us can drive automobiles with a reasonable amount of education and training. For this reason, we can also drive someone else's automobile. We can go to a rental car agency and get in a car we have never driven before and drive off the lot with some minimal acceptable level of training. This is what Rutkowski has proposed. The key concepts are the evolution of components to achieve some standardized degree of usability. As a side note, from the period of enthusiast through to the consumer period, some hybrid designs emerged. Hybrid automobiles showed up around the turn of the century. Some cars were steered with mechanisms like a boat tiller, and other cars were steered with reins, like a horse and buggy. The brakes were not always on the floor. Initially, some braking mechanisms were levers on the side of the automobile, just like they had been on buggies. Throttles were not initially accelerator pedals on the floor. They were levers on the steering column. So you see, hybrid designs came about as designers tried new technologies and different components looking for the right combination. You can see some of this in the computer industry today. There are intelligent typewriters that have small displays that show the last few lines of text. There are also CRTs that have typewriter platens built into the top, so you can put a sheet of paper in and use it like a typewriter. These are some examples of hybrid designs that I think indicate we are somewhere between the enthusiast phase and the consumer phase in the evolution of personal computers. Rutkowski proposed that products become accepted by the consumer marketplace when they achieve a degree of stabilization of their architecture that is based on definition of standard components and standard relationships between those components. Using the automobile analogy, we have evolved to today's form of the brakes, accelerator, clutch, and gear shift. And we understand how these components are used together in driving. They may vary slightly from one automobile to the next, for example, where the gear shift is located. It may be on the column in some cars and on the floor in others, but its relationship to the clutch for shifting remains the same. And we all know that when you turn the steering wheel clockwise, the car goes to the right and vice versa. So what has happened with the automobile is a high degree of architectural stabilization. These standardized components allow us to fairly easily switch from one automobile to another. There are clearly physical distinctions between automobiles, and you can all think of personal experiences where some of these differences caused you some trouble. You can understand that these differences have varying impacts on the transfer of our knowledge from one situation to another. That is one of the important things that CUA tries to understand and come to grips with. That is, what are the most important factors in standardizing an architecture, and what are the less important factors? Let's pause for a moment and see if you have any questions about the evolution of consumer products. We're going to talk quite a bit about consistency. First, remember that consistency does not guarantee usability. Consistency is a quality that you will find in many systems that we say are highly usable. Look at why these types of interfaces have been successful and easy to learn. A lot of it is because of the consistency of use of particular components in their user interface. Radio buttons, push buttons, pop-up windows, and entry fields provide a standard set of components, and these components are used consistently throughout the interface. When you learn to run one application with a CUA interface, and then you switch to a new application with a CUA interface, you'll see most of the same components in that new application, and you'll already know how to do many of the common interface functions. Consistency must be discussed relative to something. Saying something is consistent is just like saying something is bigger. You have to ask, bigger than what? It is all relative, and there must be something to compare to. When we talk about consistency with respect to IBM's SAA environment, and especially CUA, we talk about it with respect to multiple dimensions. There are different dimensions in which we can evaluate the degree of consistency. Along the vertical axis, we have consistency within a product line with respect to models of the product and over time. For example, I can talk about consistency of a Model 20 with respect to a Model 10, or a Model 50 with respect to a Model 40. I can also talk about consistency of a product's Release 2 with respect to Release 1. This is often called upward compatibility. Release 2 is upward compatible if the same concepts and techniques for doing things in Release 1 map into Release 2. So they are consistent with respect to each other. Another dimension of consistency is consistency across the audience. This is shown along the horizontal axis. Here we can identify two characteristics of the audience. One is their profession, such as an accountant, a lawyer, a banker, or a graphics designer. First, we have to assess the consistency of the user interface with respect to the different professions we expect to use the interface. Is the interface appropriate for a banker also appropriate for a lawyer, an accountant, or a graphics designer? We have to address this type of consistency. The other characteristic we have to look at is user skill level. We have identified novice, casual, and expert as skill levels, but we also have to recognize that users exhibit characteristics of these three levels throughout their workday. For example, when you interact with a particular product, like a spreadsheet, you become an expert doing some things, like filling in the cells with values. You become accustomed to touch typing through that operation. So you're an expert user in filling in the cells and cursoring and typing in values and amounts and so forth. You become somewhat expert at the aspects of the application that you use frequently. You may need a little more help on other aspects that you do less frequently. You might still use the menu capabilities for printing because you never quite remember the proper command sequence. In other words, in some areas, you are a casual user and need some assistance. Finally, there are some areas of the application how to do transformations of one spreadsheet database into a database that is acceptable by another application. We have to recognize that a user interface really has to accommodate all of these levels of user skill concurrently. because any one of us exhibits all of these characteristics when we're using a particular application or set of applications. The third dimension is the one to which CUA and SAA in general are most applicable, and that is cross-systems consistency. When we talk about consistency, we do not necessarily mean exactness. Exactness is not always necessary. What's more, it's not always desired. Think back a minute to the automobile analogy. We can fairly easily go from one car to another, and much of our learning transfers from our prior experience to this new experience, the new automobile. We know that there are some fundamental concepts involved in driving an automobile that seem to transfer readily, and we are also able to deal with some differences. We know, for instance, that the location of the windshield wiper control varies from one car to the next. It may be on the dashboard in one car and may be on the steering column in another. That can give us problems. If we get into a rental car on a nice sunny day and look around to familiarize ourselves with where everything is, that can help. You might say, I'm in a rental car now. My wipers are on this lever on the right side of the column and not on the dash anymore. If it starts to rain, I might remember that. But if you don't check things out and are driving down the road in the dark and drive into a sudden thunderstorm, it might be quite disconcerting having to search for the wiper control. The point is, we know there are some factors that users tend to transfer more easily than others. No one has a good idea yet of how to quantify the effects of those factors. We do believe that the conceptual meanings of these standard components and their relationships with each other are more constant and therefore transfer learning from one environment to another. We also believe that physical characteristics, like the location of the window wiper control or the keyboard layout of a computer, are the things that will change more rapidly based on our evolving technologies. So we have to develop an architecture for our user interface that accommodates changes of those physical characteristics, but can hold the conceptual characteristics more constant to achieve transfer of learning. So with respect to the user interface, we have taken the analysis of consistency a step further. Let's pause again and see if you have any questions about the dimensions of consistency. Next, I'll talk about levels of consistency. Think of these levels of consistency with respect to three major aspects of the user interface: physical, syntactic, and semantic. Let me start with the physical level of consistency. This is a degree of consistency that has to do with the physical layout of things as determined by the hardware that you are using. On a car, it's where the turn signals or the wiper control is located. On a computer workstation, it's the keyboard, how many keys it has and where they are located. Is there a mouse, and if so, how many buttons does it have? These are the physical aspects of a system. It would be proper to say that physical consistency in this area can be exemplified by using the same keyboard across all of IBM's workstations. We have taken a step in that direction with the IBM Enhanced Keyboard, which is available on products across the three SAA environments. But here are some problems with that keyboard. As you may know, the enter key is not in the same place in all three environments. The keyboards basically have the same number of keys with minor variations. We have not reached total consistency because the functions assigned to those keys are not consistent across the three environments. A key that takes you to the end of a line in one environment might erase to the end of line in another environment. Nevertheless, the Enhanced Keyboard is a major first step in providing physical consistency for the IBM keyboard. The next level is syntactic consistency. Syntactic consistency has to do with the sequence or order of things. In a panel of information on a workstation screen, it has to do with panel layout. This includes the location of the panel title, the location of information that tells you about scrolling, and so on. With respect to actions, syntactic consistency has to do with key sequences. For example, CUA specifies that panel titles must be centered in the first line of the panel to ensure consistency. Scrolling location information is specified to be in the upper right-hand corner of the panel. These elements of syntactic consistency are important so that users can quickly identify, recognize, and understand the role of a particular piece of information from one panel to another. When they see something centered at the top of the panel, they know what it is. They know its purpose, and they know its relationship to other panel elements. The same thing happens with the scrolling location information. Syntactic consistency helps users recognize and properly interpret what the computer is trying to tell them. Here's another example of syntactic consistency in the CUA architecture. One way to exit an application is to press F10 to switch to the action bar, press the letter X, which is a mnemonic for the exit action, to cause the exit pull-down to appear, and press X again to request the exit action from that pull-down. Or you could press the F3 key to exit. These are two techniques for requesting exit. Syntactic consistency is maintained by mapping these techniques across the three SAA environments. The highest level of consistency is semantic. This has to do with the meanings of objects and actions. Let's look at our use of exit again. CUA defines that exit always has associated with it the concept of where users are going next in the dialog and whether the data being worked on is saved or not. Whenever users see the word exit on the screen, they should now say, aha, this is my way of leaving this portion of the dialog, and the system will ask me if I need to save data if I haven't recently done so. The physical and syntactic aspects of the user interface are most likely to change as technology evolves. Obviously, the physical aspect will change as workstation hardware changes and new input techniques like voice evolve. We're definitely going to see an effect in the physical implementation, which will affect physical consistency. In the syntactic area, the effects are seen at the programming level. Software designers now work with key sequences, which are simply the sequences of keystrokes on the physical keyboard. If there is a voice capability added to a workstation, then software designers will have to define the syntactic aspects of using voice. Do users just say the name of the action, or do they have to say the name of the action and then enter? What if there are parameters that have to follow the action? How will the system know users are done giving it the parameters, and how will it know to fill in the default parameters for the ones not mentioned? These will all be syntactic considerations. As new technologies arise, they will be folded into the CUA architecture to ensure their consistent use. This will happen after people start using the technology and we can determine the aspects of consistency that need to be defined for our products. You can probably recognize by now that the semantic considerations are the ones that we can hold most constant across these evolving technologies. The physical workstation hardware will change, and different syntactic techniques can be used, such as a function key, a mnemonic, typing the command, using a mouse, or using a voice command. If the semantics stay constant, that is, if exit means the same thing and users know the system will prompt them to save or not, regardless of the technique used, then users should be able to transfer their knowledge of how to get out of an application across other applications or systems. This is one of the goals of CUA. Once again, let's pause and see if you have any questions about the levels of consistency. It often helps when we're dealing with an area like user interface design to develop a model to use as a framework to discuss the components and their relationships. This model is suggested by John Bennett of the IBM Almaden Research Center in Santa Teresa. You can find information about this model in an article called Tools for Building Advanced User Interfaces in the IBM Systems Journal, Volume 25, Number 3. Basically, there are three components of this model. There's a presentation language, an action language, and the user's conceptual model. We talk about presentation and action as languages. We use that analogy because there are a common set of elements that are used in the presentation and action languages that are analogous to words used in human language. There is a syntax for combining the elements into useful communications, analogous to sentences, and there are guidelines for the exchange of information between users and the application that are analogous to the guidelines used in the dialogues between people. So the goal for the application is to present information to users on the screen in such a way as to facilitate their interpretation of that information. If users interpret it correctly, they can then formulate the proper response to accomplish their goal. The presentation language is a result of the computer performing data accesses and computation for users and then translating that information into a form suitable for displaying to users. The action language is the way users respond. It has to do with action techniques and terms we use like exit, cancel, send, print, and file. Like the presentation language, there are elements here analogous to words, and there are ways to combine those elements into proper sequences of action requests to accomplish a user's particular goal. Thirdly, there is the user's conceptual model. The idea is that when users work with computer systems, their interpretations of what they see and how they formulate their action responses are driven by the model that they have in their mind of what's going on in the computer. Now, we're not talking about a conscious model. This is typically a very subconscious model that is derived from experiences in the real world and experiences with other computer systems, if there are any. For example, if you use IBM systems very much, part of your model is the enter key. You know that you interact with the system, and at some point you press the enter key. That is your way of saying, okay, computer, it is your turn to talk. I am through talking now. There are other models. Some don't include an enter key. People bring their past experiences to bear in any new situation. If they don't have past experience with a computer, they look to other similar experiences, like interactions with push buttons on a microwave oven or a soft drink machine. That's one reason why you see the advent of metaphoric interfaces. A user interface may use push buttons. Push buttons are like buttons on a vending machine. You push a button and something happens. Radio buttons are used in a group. It's a way to pick one selection out of the group. So if one button is pushed in, the previous pushed in button pops out, just like radio buttons on manual-style car radios. These metaphoric approaches take advantage of users' existing conceptual models from the physical world. That's why these user interfaces tend to be successful when used by people who were not previous computer users. They use a lot of the same concepts that users are already familiar with. You will see a lot of these kinds of concepts throughout the new user interfaces. The point is that users subconsciously apply their model to map their goals into an action plan. Users have to look at what is on the display, properly interpret it, and translate their goals into the proper action language responses to achieve their goal. They must do that for each individual interaction and also for the entire series of interactions to accomplish their goal. Consistency in the user interface will facilitate this mapping. For example, users look at information displayed on a screen and interpret it in a certain way, formulate a response that they believe is what they need to do next, and give that action request to the system. If they get the response they expect, then go to another aspect of using the system, see the same thing on the screen and say, oh, I've seen that before, I know what I need to do here. Give the same action request and see the same response, they'll say, aha, it did exactly what I thought it was going to do. It's predictable. I understood it. I'm learning how to use this thing. On the other hand, if they see something on the screen, take a certain action, see a response, then go to another aspect of using that system, see the same thing on the screen, give the same action request, and see a different response, then they're surprised, confused, and upset. They say, wait a minute, I thought I was learning how to use this thing. I expected to see X, it responded with Y. I'm missing something here. I don't understand how this works. And they tend to develop what have been called superstitious explanations for why these things happen. They rationalize why the system seemed to act inconsistently. Usually there is not a rational reason for the difference. It's some arbitrary difference that the designer left in the system or never recognized. But users will develop rationalizations that then become part of their conceptual model, and later on they'll try to apply that rationalization in using other aspects of the system. They have not learned how to use that system properly because it wasn't consistent, and it failed to reinforce a consistent and cohesive concept. What we have tried to do in developing the CUA is apply what we've learned in working on the user interface architecture over several years with respect to these concepts I've just talked about. We have reinforced the importance of the different levels of consistency. We have tried to hold the conceptual level relatively constant across evolving technology and still allow technology to evolve so that we can take advantage of new capabilities. CUA covers the elements shown in this chart. This is only the first level of CUA. This level is just a starting point. It's the base from which we are going to evolve. We're going to expand the scope of CUA by adding new elements to CUA and incorporating new technology. We're working on technology in two areas. We're obviously going to support new input-output technologies as they become practical. For example, voice, gestural manipulation, and artificial intelligence techniques might be added to CUA. We will also expand in other areas of user interface technology. As we better understand what users find easy to learn and what they find difficult to learn, we will address those concepts in CUA. This includes metaphors, icons, direct manipulation, and so forth. So you see, CUA is definitely intended to be an evolving user interface. CUA specifies for application designers several levels of information to be used during application design. One of the most important levels is the semantic level. We define the conceptual structure of panels. For instance, a panel consists basically of an action bar, a panel body area, and a function key area. Obviously, we go into much more detail in the CUA specification to describe the uses and relationships of these areas. We also go into detail at the syntactic level and to some degree at the physical level. We do not really have much influence over workstation hardware, but we do address how keyboard keys should be mapped, given a particular keyboard, how the mouse buttons are to be used, given a particular mouse, and so forth. So CUA defines the semantic level aspects, the syntactic level, and acknowledges and tells you how to use the physical level. We try to point out to application designers that they need to understand these three levels because they need to apply that same level of analysis in designing applications. CUA is the frame around the picture. In an application, for example a spreadsheet, the spreadsheet itself is the picture that includes how the cells work, how to reformat the spreadsheet, how to move data around, how to shift columns, etc. Typically, users are going to spend most of their time doing application tasks. So you need to think about these same factors that we have thought about in developing CUA and apply them in the same way in your application design. You need to define the fundamental elements at the conceptual level so that as technology evolves, the concepts that users learn in using your spreadsheet application are portable to the next version of your application, which may run on different hardware. CUA has taken these levels of consistency and already done some of the mapping from the definition of concepts all the way through to the design rules to tell you what they should look like and how they should behave on the display. In this way, we can get a broad degree of consistency with a building block approach using a particular set of components that can be used to design all applications. Now is a good time to pause and see if you have any questions about the CUA elements and panel areas. Lastly, I'd like to talk about how CUA fits into the overall application design process. To do that, I've characterized application design as being at 4 levels. The highest level is identifying the application task to be performed. Ideally, the way you do that is with a task analysis or user-driven approach. This ensures that you understand the user's physical environment and what the objects and actions are that users deal with. In an office environment, people deal with memos, files of telephone numbers, names and addresses, and so forth. The actions users do are edit text documents, file things, and send things from one place to another. These are the objects and actions users work with, and they are totally independent of the computer environment. Formatting a diskette is not a user action. Cursoring is not a user action. That is extra baggage that users have to bring along with them because they're using a computer to do their task. So it is very important to look at the application task level where you try to understand users, their skill levels, and the tasks that they are trying to perform before you begin the design work on your user interface. At the next level, you would get into designing your dialogue sequences. Here you define how you will present and sequence the tasks that are available to users. Are you going to allow them to do things like go through a print sequence, through an edit sequence? What do they have to do to send a document from one place to another? You must map these tasks into particular dialog sequences on the computer and construct navigation flowcharts. The next level is what are the interface components going to be. When users say, I want to send a document, how are you going to do that? Are you going to use a pop-up window? Are you going to have some radio buttons for selecting whether they want confirmation on delivery, an acknowledgement response, or if it's a personal or classified document? Here you start to get down to the user interface components you are going to use to present the dialog to accomplish the task. At the lowest level are the actual display primitives. What is that pop-up window going to look like? Are you going to map it on the screen with pels because you're using a graphical tool to present it? Are you going to use little round circles with black dots in them to represent radio buttons? Are you going to use ovals to represent push buttons? What does scrolling information look like? Is it going to be textual or graphical? That is it going to say line 1 of 35, or is it going to be a scroll bar? On this chart, I have also shown you how the tools that are planned within SAA map to those levels of application design. They really overlap these boundary areas. For example, the OS2 Presentation Manager will implement some of the primitives for the display formatting. If you use the Presentation Manager, for example, it supplies things like radio buttons, push buttons, action bars, pull-downs, pop-up windows, and scroll bars. These are all user interface components that application developers will not have to develop on their own. They will be available in the Presentation Manager as programming tools. The Dialog Manager also covers some of these components. It provides things like the function key area, and it provides dialog sequences such as help. The Dialog Manager will provide the ability for users to request help, and then it will provide a help panel sequence with an index, help on the application keys, and so forth. At the highest level, we have application generators that actually help the application designer with the application level task description, etc. On the left of the chart, you also see that CUA spans this entire spectrum of application design. There are rules that apply at all these different levels. It should become obvious to you that as the Presentation Manager and the Dialog Manager become fully implemented, they will automatically provide much of the CUA support for you. When the Presentation Manager and Dialog Manager are both available, they will support more than half of the current CUA rules. What you will see at that point in time is that CUA will evolve away from being a detailed specification of rules, and it will become more a set of guidelines and how to use these user interface components provided by the Dialog Manager and Presentation Manager. CUA right now is a very detailed, rule-oriented document because it must contain that level of detail to support tool development. CUA might also be extended to address common application styles and dialogs such as saving data, printing, and listing collections of things like files. CUA will become more of a guidelines document when most of the rules are implemented via the tools. This is the ideal situation. This gives the application designer a productivity benefit by using the tool, and, as shown on the right of the chart, it increases CUA user interface consistency automatically as the developers use the available tools. In conclusion, we have briefly looked at the background and the philosophy behind the development of the Common User Access Interface. I hope this information has expanded your view of user interface design and given you an idea of where IBM is headed in the future. In this course, you'll gain even more knowledge about applying CUA. You'll also learn more about how CUA affects the application design and development process. Thank you for your attention.